Hello everybody, welcome to this video about a formal definition of integrals. It's going to be a pretty informal formal definition. But anyway, okay, so before we get into integrals, I want to go back to when we very first started doing derivatives, way back at the beginning of the year, before we knew all the derivative rules, and we were just trying to figure out what does a derivative mean. Okay, so back then we had this function. It maybe looked something like this, and we were trying to find the rate of change of this function at a specific point. And back at the beginning of the year, we didn't know how to do that. The only functions we knew how to find the rate of change of were lines. The rate of change of this function is changing all the time, and so we had to figure out some way to figure out the rate of change at this specific point A. At this value x1. So what we did is we used the we took another point B, and we found the average rate of change between those 2 points. So the slope of the line connecting these. So we found the secant line, and then we found the slope of that, and we found. So let's say this point B was at x2. The average rate of change between those 2 points. So f of x2 minus f of x1 over x2 minus x1. So this is just the formula for slope. So that's where we started in our quest to find an expression for the instantaneous rate of change at A. And then what we did is we said, okay, well, we can improve our estimate of the rate of change at A by moving point B a little bit closer to A. So we might say, okay, I'm going to move to here. And so this distance between x1, where I'm trying to find the instantaneous rate of change, and the second point is smaller. So this little distance, delta x, was a little bit smaller. So when you connect those two points to make a secant line, the rate of change of that secant line is closer to the rate of change actually at A. So down here, this will, the denominator is delta x, that's how far away from x1 we are. And then we said, okay, well, we can always get a little bit closer. And so the formal definition of a derivative was, okay, well, let's use a limit process and see what is the value of this rate of change approaching as delta x goes to 0. So as point B gets infinitely close to point A. And so by letting that second point in the definition of average rate of change approach exactly where the first point was, and looking at that limit process of making the distance between them smaller and smaller, we were able to come up with a formal definition for derivatives. So if you remember back then, you all loved these problems where you'd have something like find the limit of as delta x goes to 0 of x plus delta x cubed minus x cubed all over delta x or something like that. And you'd have to recognize, oh, that's the formal definition of derivative, da, 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 da. And then we went on to do a bunch of shortcut derivative rules that made this easier. But the important part is that the formal definition of a derivative comes from a limit where we are taking 2 points, finding the average rate of change, and then using a limit process, making the distance between them smaller and smaller. So we're also going to use a limit process to define an integral. Okay, but here the problem is slightly different. So here we're trying to estimate the area under a curve. As we've been seeing, we are going to try to estimate that by making some rectangles underneath the curve. Here I have 4 rectangles. It's not a super great fit. Now this is a function y equals square root of x, by the way. So how can we improve the estimate? Well, we can improve the estimate by increasing the number of rectangles, like so. As you can see down here, I have a math expression for finding a sum. A lot of times in the formal definition of an integral, you're going to see the summation operator. It's we'll talk about it more in class, but it really just means I'm adding up the area of a bunch of different rectangles. Of course, I can make my estimate even better by making even more rectangles. So here you can ignore all this insane writing up here. And so, how could we ideally get our best estimate? Well, so here's where the limit process comes in. If I could take the limit and let the number of rectangles go to infinity, which is the same way of saying let their width go to 0. So notice every time we have more rectangles, they get skinnier and skinnier. So here, if we can make the rectangles get infinitely skinny and have an infinite number of them, we would be able to estimate the area exactly. So in fact, the formal definition of an integral, or the formal definition of the area under a curve, is the limit as delta x. So here delta x is the width of each rectangle you're using. So as the width of each rectangle goes to 0, right? So there's the width. What will the area under the curve be? So there is a math operator that stands for this process. So there's an example in this PowerPoint of how to go through a process for a very simple function. Even doing the formal definition of integral for a very simple function is actually very complicated, and I don't want to get into it in this video. I just want to go over some of the basic notation. Please feel free to take a look at it if you want. We'll talk about what you need to know from it in class. But anyway, so the stuff you do need to know is here. So this operator, the integral operator, looks like a long skinny S, and it is in fact based on the word sum. So that's a good way to remember what integration is we are adding up an infinite number of infinitely skinny rectangles. There might be numbers above and below the integral operator. That means from A to B. So if I was trying to find the area underneath this curve, let's say this was, negative x times x minus 4, something like that. From 0 to 4, the range I'm looking at is 0, so the number down at the bottom of the integral would be 0, and the top number would be 4. These are called the bounds of integration. It says where do we want to start finding the area and when do we want to stop finding the area. And then the actual function comes next. And then dx. So this dx is not going to be part of any of the computations you do. This whole setup here is shorthand for finding the area of rectangles. So if you think about it, this is the height of each rectangle. So if you imagine that we are finding the area of this area under this curve by finding the area of an infinite number of infinitely skinny rectangles, then what we're doing is just finding the height at each one of these points. The height at each one of these points is negative x times x minus 4. Okay. So we're basically finding each value of this function in between 0 and 4 and adding them up. Dx represents the tiny, tiny sliver of width that they have, that each line has. It is what happens to delta x from the summation notation when we take a limit and make the rectangles infinitely skinny. So this is just like a stand-in for the width, and I'm going to put width in quotes here, because once we take the limit and have an infinite number of rectangles under here, the rectangles don't have width anymore. But the point is, the dx, you won't be multiplying anything by it. It doesn't stand for anything that you need to deal with. It just appears in any integration problem. So this operator that you see here, what it is asking me to do is take the function 2x and find the area underneath 2x in between 0 and 2. This is very easy to do. This is just a triangle. The base is 2, the height is 4. You get 4. But the important part is that you understand what the notation here means. So, integral means find the area underneath, or find a function that expresses the area in between x equals 0 and x equals 2 of the function 2x. In the next PowerPoint, we're going to talk about how do we actually do this more, but right now you just need to understand what the notation means. Okay, so if you saw something that looked like this, this would mean find the area underneath the sine curve in between x equals -1 and x equals 5. So sine is going to look something like this. So find all this area in here. And so on and so forth. Okay, so this is just to help you understand, like, what does the integral operator mean? It means we're adding up the quote-unquote area of an infinite number of infinitely skinny rectangles. So it's what happens, it's the sum that we get for the area under a curve when we let our number of rectangles go to infinity. And that this, so this is a new operator, this is new notation for you all, that's what this notation means. So the integral operator means we are summing up all those infinitely skinny rectangles. And if there are bounds of integration, so remember these numbers are called the bounds of integration, that tells you where under the curve we're trying to find the area. Okay, so we'll get into techniques to actually do this in the next video, but that's just some good notation and conceptually what the integral operator means and formally how it is rooted in a limit process. Okay, cool. Talk to you later.